Hello everyone. Let us now discuss today's POTD problem, count good triplets in an array. Before starting the question explanation, if you like this video, do share it to friends because this is a super hard to me and it has took over 2.5 hours of understanding this question. So if you like this video and my explanation, do subscribe to my channel. So we are going with two indexed, zero indexed arrays. Now nums1 and nums2 of both length n, both of which are permutations of 0 to n minus 1. That means if we have array of size 4, that means 0, 1, 2, 3 are these elements are permutations. So if we do some rearrangements, then we got these two arrays nums1 and nums2. So if I got n, that means I will have only values from 0 to n minus 1. That is the first observation. A good triplet is a set of three distinct values which are present in increasing order by position both in nums1 and nums2. In other words, if we consider position 1 of v as the index of value v in nums1 and position 2 of v as the index of value v in nums2, then a good triplet will be a set x, y, z where x is greater than or equal to 0, y and z are less than or equal to n minus 1, such that position 1 of x is less than position 1 of y is less than position 1 of z. And position 1 of x is less than position 2 of y and position 2 of z. Return total number of good triplets. Now let us see, firstly, let us see the example 2, 0, 1, 3. 0, 1, 2, 3. So here there are four triplets. Don't look at these triplets, but let us see what are the triplets which is okay. That means which is a good triplet. 0, 1, 3. These are x, y and z. Let us see how. 0, 1, 3. Right. 0 is coming before 1, 1 is coming before 3, and so in the same 0 is coming before 1, 1 is coming before 3. That's it. This is the only good triplet. But let us go to the next example. Here we'll start with our explanation of the problem. Now, I don't need to get through a triplet here and also triplet here, so that to get what I need to say is to get only one traversal, then I need to get the answer. That means I no need to traverse these two arrays to get the answer. I want to traverse one array so that I will get the answer. Now, 0, 1, 2, 3 and 4. Let us see. Here 4 nums1 in nums1 4 is present at index 0, but 4 is present in nums2 at which index it is present. I'll write it over here. Let me name it as mapped. Okay, mapped. Here this array stores where the value is present, at which index the value is present in nums2. It is present at 0. Okay, I'll write it 0. Here I got value as 0. Where 0 is present in nums2, it is present at 2. So I'll write it over here. Now I have the value of 1. Where 1 is present in nums2, the index is 1. I'll write here. Now where 3 is present at an index in nums2, which index it is present at 4. I'll write here. Now, where 2 is present at an index, which index 2 is present in nums2? It is at 3. So, in this array, if I get a triplet, that means if I get x, y and z such that x is lesser than y and y is lesser than z, then this is a good triplet. Let us see how. If you doubt, then let me do a check on this. I have 0, 2, 4 and 3. So I'll write it 0, 2, 4. It is x, y, z. X is lesser than y. Y is lesser than z. Okay. Good. Now 0, 2, 3. Is it okay? Yes. 0 is lesser than 2, 2 is lesser than 3. Perfectly alright. 0, 2, 4. Wait a second. 0, 2, 4. 0, 2, 3. And I also have 0, 1, 4. So 0, 1, 3 is also another one. 0, 1, 4. 0, 1, 3 is another one. So if you check here, output is 4. That's it. So our algorithm is working beautifully, right? Our intuition is good that I got 4 as the answer for the second example. Now my question is, here I have 0, 2, 1, 4, 3, right? I have 0, 2, 1, 4, 3. Don't look at these bit and other things. Look at 0, 2, 1, 4, 3. At this index, if I have the number of elements which are lesser than 2 at the left, that is what I need. I need x, y, and z for, wait a second. For every y, I need the number of elements which are lesser than y. I need the number of elements which are greater than y, which are called z. The number of elements which are lesser than y is called x, right? So what my intuition is, I will traverse from I index I is equal to 1 to lesser than n minus 1 and make it or assume it as y, and I need the elements, the number of elements which are lesser than y, till that index, not from whole the array. Don't get confused. I need the elements which are lesser than the current value before that index. So if I am at, so here I am writing y. If I am at this index 1 here, right? I need to check from this array how many elements are lesser than this value 1. How many elements are lesser than 1? 0. Sorry, 0 is lesser than 1. So the number of elements which are lesser than 1 is 1. Now, the number of elements which are greater than 1 in this subarray, that means after this index 3 and 4, 2. So what I'll do is for this index, for this one, I have two answers, 1 into 2. That is 2 answers. If you doubt, check it. So for y is equal to 1, I have 2 answers. That's it. I need my intuition. I am writing here. My intuition is getting the number of elements lesser than current value uh, before before this current index. I think this description is somewhat confusing, right? Here I need the elements which are lesser than the current element and left, and they are to the left. So and also getting the number of elements greater than current value after the current index, or let me tell it as to the right. That's it. And here to the left. The problem here is, here the problem is I can use something like a Fenwick tree. So I will explain you how does this Fenwick tree also works. So first thing, let us be clear that how does I can compute the number of elements lesser than the current element and to the left, the number of elements greater than the current element and they are to the right. Now, what does this bit represent? I'll also write it here. Here, bit represent the number of times value is occurred. Now, you can imagine it as frequency, but we are doing this as we traverse the array, not not pre-computing the whole array. So this is simple and clear. So imagine it as a frequency and we are not pre-computing this frequency before traversing. So while we are traversing this array, then only we are incrementing the bit, this array. So let us see how we are incrementing it. So everything is initialized as 0. How do I know that bit is only for size 5? Because we are given with an array of size n. That's it. So everything is initialized to 0. I am assuming that 0 is present for 0 times, 1 is present for 0 times, 2 is present for 0 times, 3 and 4 same. Now I am at 0. What I see is here I am taking this left smaller is nothing but index 0. Index 0. What does this left smaller stores? Left, wait a second, left smaller stores the number of elements lesser than lesser lesser than current element, and they are to the left, right? And also I will store this right greater. Now, what does this right greater stores? The number of elements greater than current element, and they are to the right of current index. So they are to the left of current index. So this is clear. I think it is clear to left smaller and right smaller. So at index 0, I will store the number of elements which are lesser than the value at this index in this array. So the number of elements lesser than here, the number of elements here. Instead, I am storing that x here. That's it. In the right smaller, I'll store z value. That's it. So simply I'll multiply x and z and compute the sum at the last. That's the whole intuition for this question. Right. Now, the problem here, the problem here is something like I have 0 now. Now, what I'll do is bit will be incremented by 1. Now, I have left small. What I'll do? The number of times this left smaller is nothing but here I have 0. 0. Imagine I am having 3. Imagine I am having 3. So if I have 3, that means left smaller for that index will be, I'll tell you what will we will be doing here. So I am having 3 as the value. Now I need the number of times the numbers something like value minus 1 is occurring, right? Value minus 2 is occurring. The number of times value minus 1, value minus 2, value minus 3, value minus 4, all these are what is the number of times they are occurring. This is what I need. So if I got it, so if I got 0 is present for one time and 1 is present for 0 times and 2 is present for 1 time, what does this mean? I have 0, I have 2 and I have 3 here. So when I am at this index, I will compute these all values, 2 and then 0, all this sum here. So 0 is present for 1 time, 1 is present for 0 times, 2 is present for 1 time. So the number of times 3 is present is only 1 time, but I get left smaller of 3 will be 2. That's the whole intuition for this question, right? Now I have 1 left smaller of 0 is computed as value minus 1. Value value is 0, value minus 1 will be minus 1. I don't have any values like this, so left smaller will be 0. Now bit of 0 is incremented by 1. That means 0 is present till now for one time. Let me go to the next index 2, right? So 2 is present for how many times? So before that I need to compute how many times lesser than these 1 and 0 are present, right? I have value as 2 right now. So I need how many times 0 is occurring, how many times 1 is occurring. 0 is occurring for one time and 1 is occurring for 0 times. So I sum up this and I have the number of times value is 2. So left smaller of 2 is 0 plus 1. That means 1. Left smaller of 2 is 1. Sorry. Left smaller of index, right? Sorry for the confusion here. It will be 2. Left smaller of 2 will be, that means here the index is 2. The number of elements which are lesser than the current element will be stored in the index. So that's why I wrote here the index. So this represent the number of elements which are lesser than the element at this index and to the left. So don't get confused. Sorry for the confusion I created. So right, I have 2. That means I am at index 1. I need to change left smaller of 1. A number of times the values lesser than 2 are occurring till now in the array, which is only 1 plus 0. So I have 2. So I will compute the sum from 0 and till 2 minus 1. 0 and 1, if I get the sum, it is only 1. So till now I have 1 as the number of lesser elements than this one. Now index 1, right? I am going to index 2. I have 1. But before going to index 1, I need to do something, which is this need to be changed, right? So if I want to change it, I am changing it something like here. 2 is occurred for one time. Now I am at index 1. So value is 1 and value minus 1 is 0. So I need the number of times I got 0. It is just 1. So here 1. That means at till this index 2, I have only one element which is lesser. That's it. Don't get confused. As I said, I have confused you somewhat, right? By confusing this with the index and value. So now I have 1, right? 1 is present for how many times? One time. I am just incrementing. Now I am going 4. I have 4. What I need? I need the number of times 0 is occurring. Wait a second. Number of times 0 is occurring. Number of times 1 is occurring. Number of times 2 is occurring. The number of times 3 is occurring. So, number of times 0 is occurring is 1. Number of times 1 is occurring is 1. And then 1 and then 0. Totally 3. I'll write 3 here. That's it. Now, 4 is present for one time. So what I'll do, I'll just mark it as increment the count as 1. That means I'm just counting the frequency. I go to the next element 3. What I need? I just need, wait a second. I just need how many times I got 0, how many times I got 1, how many times I got 2. I got 0 for one time, 1 for one time, and 2 for one time. If I compute all this, I'll get a sum of 3. So at index 4, the number of elements lesser than 3. So don't get confused. The number of elements lesser than this. Simply write it as the number of x values are 3 for index 4. That's it. X values. That's it. Right. Now, I think you can compute the greater. Right greater. So I will explain you how does this Fenwick tree works by taking a prefix sum approach, right? Imagine you are having an array like 2, 4, 5, 6. 6, 1, and then 3. This is the array you are given with. Now you have something like this is the array. Now I need the sum. The sum is nothing but 2 and then 6 and then 11. 11 plus 6 is nothing but 17. 17 plus 1 is 18. 18 plus 3 is 21. Now I need the sum from 0, 1, 2, 3, 4, 5. Now imagine if I want a sum. This is a clear prefix sum array. So I add 2 to 4 and I got 6. I add 6 to 5, then I get 11. 11 to 6, then I get 17. 17 to 1, I get 18. 18 plus 3, 21. This is the prefix sum array. But imagine I have changed. But before that, imagine I have changed 5 to 6, just added 1. So what I need to do here, so it will be 12, it will be 12, and then I need to add this to every element after this, and here it would be 19 and here it would be 22. Okay, what the time it is taking, q into n every time. So this is wrong. Why? Because this is something like, it is not wrong, especially that it is will be in the error of time limit. So the time limit will be exceeded. That's what I want to say. But what if I store these elements as something like, I have 2, I have 4, I have 5, I have 6, and I have 1, and I have 3, right? 2 is present at index 0, 1, 2, 3, 4, and then 5. How do you represent 0? 0 is represented as 0, 0, 0. 1 is represented as 1. But if I change it as one indexed array, so I am removing this and just placing it here. So I am thinking this as one indexed array. So what will be the binary representation for 1? Just double zero 1. Now what will be the binary representation for 2? 0, 1, 0. What is the binary representation for 3? 0, 1, 1. For 4, 1, 0, 0. For 5, 1, 0, 1. For 6, 1, 1, and 0. What I am doing is just group these elements like I have 1. Okay, I have 1 here, and I also have this 1. So if you see, these are the elements, right? They make a group. So I am telling that 2 and then 3 and then 4, 5 and then 6. Now I have 2 here, here, and then here. So this, I think something like it makes a group. This is what Fenwick discovered. So I have 4, I have this one, and then this one. So this for ones, this for ones, and this for ones. So this is the first group, this is the second group, and this is the third group. Let me construct a tree out of this. So I am searching for something like, at what are those indices which are having the zeroth index as 1 as a set bit, that is 1, 3, and 5. Okay, 1, 3, and 5 are having zeroth index as set bit. Now what are those indices which are having uh, 1 index as set bit? 2, 3, and then 6. 2, 3, and then 6. 4, 5, 6 are the elements which are set bit at index 2. Okay, this is what we create a Fenwick tree, binary index tree. But don't be involved in this tree. What I say is, involved in something like, I am taking 1, right? So just take these elements and just I am copying it. So I have 1. So what is the least significant bit? 0. 0. The least significant bit is 1. I'll construct a binary number. So this is 1 and I am adding 1 to it, the least significant bit to it. So I will get 1 plus 1 is 2. So I will add here 1 plus 1 then 2. So I have 0, 1, 0, right? The least significant bit is 1. So I am adding something like the least significant bit and I'll get 4, 1, 0, 0, and if I add the least significant bit again, I'll end up in 8, which goes out of bounds. What I am doing is when I call for a update in Fenwick tree, update the index, wait a second, update index, comma, value for prefix sum. I am not talking about the question which is given for us, count good triplets. I am talking about update index comma value. So it will take index and add least significant bit to it and add the value until until so least significant bit to it and make this index is equal to index and something like a binary operation, right? And this loop will end if index goes out of bounds. So when index goes out of bounds, add a least significant bit until index is lesser than the bound. So after we are taking the least significant bit, but before that add value to the index. So let us see how we can do this. So wait a second. Here I am having at index 1 2 3 4 5 6, right? If I write it in a linear manner, right? Now I have 2 4 5 6 1 3. I am talking about the prefix some question, something like it, to make you understand how does this Fenwick tree works. So I have 2 4 5 1 3. I am taking this as indices 1 2 3 4 5 and then 6. I'm just taking the prefix sum as something like I'm going and adding the least significant bit to every index. So I am at 1. Now I am adding the value here. If I add, I have 1. That means 0, 0, 1. If I add the least significant bit plus 1, I will end up in 2. So 0, 1, 0. If I add the least significant bit again, but before that, as I said, at index 2, the index where we got, I need to add to the value. If I add, simply it will be 0 everywhere. So instead of writing zeros, I am writing 2 here. I am skipping writing of zeros. Now I have plus 2 and I ended up at 1, 0, 0. The least significant bit is 4 and I will end up at out of bounds. But before that, 4 added with the value. Now put it aside and do it again for index 2. Index 2 is having 0, 1, 0. If I add the least significant bit again, I will be ending up at 4. But before that, add this value at index 2, add this 4 to 2, then I'll get 4 plus 2 will be 6, right? Okay. 1, 0, 0. I got 4. So if I add 4, the value is added to the index. So if I add 4 here, I am at 2. So if I add 4 to 2, I end up with 6. Okay. Now, if I add a least significant bit to 4, I'll end up at 8. So I'm skipping that again. Now I have 3. 3 is represented in binary as 0, 1, 1. If I add the least significant bit, it is 1. So if I add 1, I'll end up in 4. But before that, 3 should be added with 5. So before that 5 is added, then I got 4. Then I have 1, 0, 0. So 4 I need to add with 5 and I will get 11. Now, I'll tell you how you get the array, the prefix array, and also how you get the sum between two indices. Now, let us go to the next index 4. So simply I am putting this aside, right? 4 is having 1, 0, 0. So at 4 I am adding the value of 6. The value is added, then I'll get 6 plus 11 is 17. Now I am going to 5. Then let me put it aside. Why? Because if I add a least significant bit of to 4, then I'll end up 8. So no need to check that again. 5 is the value for 1. Sorry, 1 is the value for 5. If I represent 1, 0, 1 is for 5. So plus 1 will give me 6 and 4, 2, 0, 6. And if I add 2, I'll end up in 8. So let me stop it. But 5, I am adding 1, and for 6, I am adding 1. Now let me go to the another index 6. Let me put this aside. Here I have 6 and I am adding 3. So 6 and 1, 1, 0. At 6 I am adding the value. I'll get 3, right? I'll get 3 here. Now I have plus 2. I'll end up in 8. So let me stop it here. Now what is the prefix sum till this 6? If you want 6, then I will remove the least significant bit and add all those indices till there. So this is how the Fenwick tree approach works. So the same of adding the least significant bit and storing them will be used in this question, and will store that left smaller and also bit in the same way. So this is how you solve this problem, and I have given the code links in C++, Python and also Java in the link in the description. Go and check it. But update I plus plus, as I said, I is less than or is equal to size, then bit of I plus is equal to delta. I this is nothing but we are doing I is added the least significant bit. That's it. Now query is nothing but the number of bits or something like the number of elements lesser than the current element till the current till the index. So this is how you solve this problem. You just compute result plus is equal to left count of I into right count of I. Left tree dot update. Update is used as I said. So I'll take the least significant bit and add to the index. So if you like this video, do share to friends, and you have any queries, and if you haven't understand anything in the middle, then do comment in the comment section. Thank you.